Okay, recording and transcription started. And let me now go in the page, our web page. And let me click again, let me take again the link, the climate change problem, because if I will remember, we had a couple of additional issues to discuss. And so last time we got to this figure. I used the PowerPoint presentation, but the figure was taken from here because we talked about the feedbacks of climate and we identified what are positive feedbacks and negative feedbacks. Please keep in mind the difference and you see here in this figure that negative feedbacks are those that are beneficial. So don't get misled by the term negative. Negative means that it's decreasing the warming, reduce the warming, as you can see in the figure. Okay, let me just check the chat. Yeah, if I want to highlight the chat 1 second, because I have another screen, so I can keep the chat visible. Okay, good. Here. Perfect. So negative means that warming is reduced, the effect of climate change is reduced. A positive feedback is self-reinforcing, so it means that it is self-exciting. It's warming induces additional warming. Let's skip this box here because I want to focus on it, but later. And let's now talk about the question of climate change attribution. This is a relevant scientific question. At the beginning of our discussions, our lectures, I said that we are not focusing on climate change attribution. Attribution means identifying the causes of climate change. The causes may be natural variability, may be anthropogenic forcing, maybe other natural effects like volcanic eruptions or solar activity that is varying, and they can be driver of climate change to different extent. Today, the scientific community recognizes that there are for sure two components, anthropogenic forcing and natural variability, that are superimposing each other. It's not yet clear what is the amount of the first and the amount of the latter. So we have not clear, depending also on the geographical location, what is the dominant, what is the dominant process, the dominant cause of climate change, which can also, I say again, depend on the location and depend on the period. So there is today the feeling that probably natural variability and anthropogenic forcing are superimposed. So they are not compensating each other. And again, attribution means estimating the causes and estimating their magnitude, their contribution. So you understand it's in view of the uncertainties that we mentioned several times, it's a relevant, challenging scientific question. Here I have two videos, you see the links, which I suggest you to see, and they are from Geoscience Video, which is a website that collects public videos on issues related to the Earth system. I just wanna click on one of these links to show you this website, and you see here from Geoscience Video there is a long list. So ice, ages and climate cycle, evidence for climate change, and sorry, because this is the list of the videos also includes some videos that I recently that are proposed to me. So let me see if I can see the list of the videos. And this is evidence for climate change, induced climate change. And the other video, ice, ages, and sorry, from Geoscience Video, this one, which I just clicked, is related to, this is advertisement, but then it's related to natural variability, ice ages. And you see here, there is the list of from geoscience video. And there are a lot of interesting videos. They are not technical, but still they are really well done. So I suggest you to have a look. Okay, but we are not looking at the videos together. And this is something for you to focus on. And as I said, and if you read here, today scientists substantially agree that human activities are impacting climate at both the local and global level. However, as more and more data and scientific results become available, it is increasingly clear that natural variability is still poorly understood, although it may potentially cause long-lasting impacts and environmental disasters. Relevant examples of phenomena that we believe are due to natural variability, among others, are offered by the so-called Dust Bowl in the United States and Canada during the 1930s, the 2000 Australian drought, and the droughts in California. So let's use this click. Let's have a look at these clicks. So I can also check if the links are still active. And here there is a nice description of the Dust Bowl, which occurred in the 1930s. You see here from 1931 through 1939. And it was a phenomenon that changed the country, the US priors, forever. And it's interesting to read the story. I just want to leave it to you. But if you read here, it's indeed an interesting story, and you can find also it on Wikipedia. If you look for dust bowls, you see that there are several links, and in Wikipedia there is another nice description of it. Okay, so this is an example. And this occurred in the 1930s. So we believe that human-induced climate change had really little to do with it. Another example, as I said, is the 2000 Australian drought. And the 2000 Australian drought is also known as the Millennium Drought, lasted for about 10 years. It was a 10-year period with about from 20 to 30% less precipitation. And then it stopped. It stopped in 2010 and with the occurrence of some floods. And in fact, today it's an active field of research to study the alternation of floods and droughts, because this could be an effect of climate change. In any case, this drought was not a phenomenon lasting forever. And at that time, they believed that it was the effect of climate change and would last forever. Actually, in 2010, it ended. And then they got another drought in 2019, I think, but after a long time. And another interesting story is the droughts in California. And also here you can find in Wikipedia, and you can see a graph of drought onset, recent drought onset from the year 2000. On the other hand, California experienced some drought also in the past. This is another example of a Wikipedia article with a warning. Okay, so insufficient documentation of the causes of the droughts, which is a clear indication that it's a challenging question. Okay, and then there is a discussion on the science of climate change. I leave this to you to read. It's just describing what are the disciplines involved and what is the role of engineering and why engineering studies also the science of climate change. The reason is that engineering is also involved in climate change adaptation and mitigation. And as you know, it's necessary if you want to solve a problem, if you want to propose a good design project, it's necessary that we know the causes and the science behind the problem. And this is why engineering is also involved. And here there is also discussion on the value of consensus. I leave it to you to read. And why this discussion? Because in climate science, consensus is often called into play to provide support to assumptions and theories. In engineering, we are not used to base our decision on consensus, but on the technical validity and therefore on testing. But engineering is an applied science. Climate science is also to some extent applied, but it's more theoretical, more blue sky, let's say, more concentrated on the understanding rather than application. And therefore, in the absence of a large enough database to make a reliable testing, this is our problem, which we mentioned several times. What we do is also to use consensus to test our assumptions and theories. Actually, it's a practice that is discussed at the global level. The call for consensus is not new in science. And, science, when in absence of data, in absence of quantitative testing, also calls into play consensus. On the other hand, from the technical point of view, we have to be very careful because we cannot justify a technical decision basing on consensus. And so the discussion is placed here because many of you are engineers, so you have to be aware of your responsibilities. The responsibility of the scientists are different from the responsibility of the technician, and the responsibility of an applied scientist is different from the responsibility of a pure scientist, pure meaning purely theoretical. And here I'm quoting the late physician, producer, and writer Michael Crichton, which in my opinion gave a nice synthesis of the risks related to consensus, to the use of consensus to support technical decisions. Okay, and then there is a discussion on tipping points, which is a repetition. Sometimes in my lectures you see repetition. I want to draw your attention on that. Of course, when you see repetitions of things that you already studied, you don't have to study them again. Sorry for the trivial suggestion. The repetition is originated by the fact that I am teaching in several degree programs and more than one university. So the selection of my lecture that I propose to different places, it's different. And therefore, in some cases, I need to present only this lecture, not the previous one. So this is why there are repetitions. Now, I want to focus on climate data because after talking of consensus, after talking of lack of data, I think it is a nice discussion if we focus on the data. The data are essential, and it's an essential method of the scientific method, the experiment. Let me take, sorry, the PowerPoint present. I think I can move forward with this because you don't have to read. It's just enough if you look at the figures. So, as I said, experiment is the basic of the scientific method. It's the base of the scientific method. And the experiment means that we need data. We collect data or we use data that were already collected to test our theories and assumptions. Keep in mind the assumptions, okay? It's very important that we know the assumptions that we rely on. We need assumptions because in order to write a model, in order to develop a model, we need assumptions that basically simplify the theoretical treatment and introduce approximations, errors, but they are needed. It is a usual practice in science to rely on assumptions. The important thing is that they are transparent, they are clear to the user, they are clear to the scientific community, so that we can judge the appropriateness of these assumptions, and we are aware of their limitations, which is essential for technical applications. by knowing the assumptions, I know the limitations of my model, I know what are the conditions that may lead to a mistaken application of the model. Okay. Now, the problem is that, as I said many times, we don't have a large database of climatic data for several reasons. We are lucky with some few spots, like what you see here. It's the daily, here is represented at the annual scale. It's annual rainfall in Bologna. And the rainfall in Bologna was monitored at daily scale from 17 something, and it is continuous from 1813, meaning that for every day from 1813, so it's 220 years of observation period. Any day we have rainfall observation in Bologna. The rain gauge was moved. This is a bit of a problem. And also the monitoring instrument was changed. This is a bit of a problem because it may introduce some dishomogeneity. On the other hand, the dishomogeneity is something that can be tolerated. There have been corrections of these dishomogeneities. And you understand that the information content that is delivered by this graph is enormous, because we can see, for instance, in gray here, the mega droughts that occurred in the past. And we can see from this series that from 1950, we didn't have any significant mega drought in Bologna, and therefore in the region, because of course droughts are not a local process. Droughts are regional. They are a regional process. So this is a lucky example, and we have in Italy some other rainfall series available, and in Genoa from 1813, in Padua from 1725. It's the longest daily rainfall series that observed in Padua in the world. So in Italy, we have this lucky situation, because in Italy, you know, there was a scientific interest related to the civilizations that populated Italy after the Romans that is long lasting. Italy has a long history, starting from the Etrurians and then the Romans and then the other dominations. And therefore it's a lucky place. And it's also lucky, Italy, because people needed to understand climate, because Italy is a bit complicated in terms of morphology and in terms of extreme event, flooding, water resources. So this is why the Romans were the first to build so important aqueducts. And this is why we have observations of rainfall data and in some cases of temperature. But as I said, this is a lucky situation. In general, we don't have so extended information. And in any case, we are talking of the past 300 years for Padua, which for climate is nothing. 300 years is 10 generations. So it's a small time also for humans, and for climate is nothing. So we need to extend this information. We need to get information on the climate of the past. And given that we don't have instrumental observation, we have to find something different, something additional. And the something additional that we found is given by proxy data. Proxy data are climate data that are not directly measured, but are derived from proxy observations. And which means proxy means that is close to it, but it's not really it. So it's not really rainfall. It's something that is close to rainfall, something that from which rainfall can be derived, but it's a proxy. So if you click on the link here, there is a definition. And for instance, you see here a reconstruction of global temperature in the past 2000 years based on putting together several different proxy, okay? And there is a description of proxy data. So you see here in the study of past climates, climate proxies are preserved physical characteristics of the past that stand in for direct meteorological measurements and enable scientists to reconstruct the climatic conditions. Examples of proxy data, ice cores. So ice cores deliver information of past temperature through their isotopic content. Isotopes are associated also to rainfall, are markers of atmospheric temperature and atmospheric composition, because of course, depending on the composition of the atmosphere, which contains these isotopes, then these isotopes are delivered to the land through rainfall and stored in the ice caps. So the ice cores are an interesting information, because you see here two different isotopes, and through the progress of the concentration of isotopes along the depth, we can reconstruct the progress in time, because the depth of the sample is related to time. The deeper the sample, the longer the time span towards the past of this information. So basically you can substitute the horizontal axis with time. And of course, you need to find a way to relate the depth to time, but we have consolidated methods to do that. And then with the change in isotope concentration, we can reconstruct the temperature. So basically, this progress of isotope concentration, which is a difference, it's a delta, and difference in isotope concentration can be associated to shift in temperature. We don't need to understand what isotopes are. They are markers, as I said, of the atmospheric composition. If you need more information, you can look on the web and you find a lot of it. It's just enough for us to know that they are useful proxy data. Another type of proxy data, you see this picture, is given by tree rings. And we know that from tree rings, we can get reconstruction of climate, typically at annual time scale or seasonal time scale. Tree rings cannot deliver information at the daily time scale. The same thing for ice cores, by the way. You get an information that is a bit smoothed in time. Smoothed means that variability may be reduced. So you may underestimate the variability of temperature, variability of rainfall, basing on proxy data. And the same thing with the tree rings. They are anyway a very useful information which we use for understanding droughts. In fact, yesterday I wanted to put two additional links here. First of all, a link of the National Ocean and Atmospheric Administration. Let me open it. And it's an interactive platform which presents, from which you can download a lot of proxy data. So basically you see the search methods, paleoclimatology interactive map, select study location by region, proximity to a point, or text-based attributes. If you click here, you get a map showing, allowing you to make the selection of the desired location. And it's a GIS, so it takes some time to load. We are not extracting data today, but I just wanted you to deliver this information, which is extremely important. And by the way, let me see, it's 95% of loading. By the way, I wanted to introduce an additional web page on my ebook on mega droughts to include these links. Here you see the locations that are starting to appear. It takes some time to load, and depending on the position over the globe, you get several different options. Okay, the system is currently unavailable, which is not a problem for us. I think you got the information. And let's now see the second link, which I think is very interesting as well. It's the Old World Drought Atlas. So this is interesting. It refers to Europe. So first of all, this atlas brings data from the year 0 to 2012. And let's see an animation. The animation doesn't say much, but it shows the progress of droughts in red over Europe a long time. You see that the reconstructed variable is the Palmer Drought Severity Index. It is an index that we use to measure droughts, and it is computed along the summer season, which for Europe is June, July, August, and you see up there reconstructed June, July, August PDSI. And you see the progress of the year, which and for each here you see the map of the Palmer Drought Severity Index. So basically, when you see red, it means that there is less rainfall. The PDSI is based on rainfall, summer rainfall. When you see red, there is, as I said, less rainfall. And then this is an animation. We can move forward. Here we are in the year 1000, and you can see the differences in the climate a long time. And now I am moving forward very quickly. There are, of course, some patterns that are frequently repeated, but in general, you see that there are some periods where the droughts are more concentrated on the west, like this 1793. And if we get to the recent years, in the recent years also, we should see that the droughts are more concentrated in the west. This is 2012, and this is 1995, etc. And also, it's possible to make this animation faster. And okay, let's move to another interesting feature of this website. Here you can get time series. So if you look at the menu time series and you click on extract, you can select what kind of time series you want. So there is the reconstructed PDSI. I'm not giving the details on how PDSI is computed. Okay, it's, as I said, it's an index of rainfall. When you have rainfall less than average, you get a negative PDSI. When rainfall is above average, and you get the yellow and orange color with less rainfall. When you are above average, PDSI is positive, and you get a blue color. So let's download the reconstructed PDSI, and let's select a single grid point. We make next, and then we get a map, and we can choose. Let me just make a zoom here, and let's choose Bologna. Okay, and here we are. Bologna. Let's put the marker over Bologna. Okay, perfect. Create time series. I'm clicking here. Error. Perfect. Let me go back and let me try again. Okay, and let me just do this. Let me just move the marker somewhere. I did it yesterday night and it was okay. Let me just try to Milan. Okay. Okay, let me just see. Let me start 2012. I'm not sure. Maybe that the mistake was that I didn't specify start and then the year. Let me put back the marker over Bologna. Now I have the starting year. It seems that now it's working. No, it's still not working. Let me just check. Let me try with a different year. Okay, this is from the year 1000. So this is a graph of the PDSI in Bologna, reconstructed, so basing on proxy data. And from the year 1000, yesterday I was able to download from the year 0, so you have to try. Of course, these websites, if some data are lacking at the desired location, may give an error without telling you what is the reason of the error, so you have to keep trying. And it's interesting here to see the last drought. It was in 1950, the last big one. And there is also the drought of 2003, I think it is this one, this very low value. And the drought of I think it is this one. Where is my mouse? The drought that occurred in 1950. It was quite long, as you see. And you can get the time series if you get download txt, and you get I was not successful for some reason, but you get a list of the data, which you can use to make some analysis. So this is definitely interesting. Let me go back to my web page now. It's here. Sorry. This is definitely interesting. Okay, I think we are done with this lecture. And before I move forward, because I want now to focus on the yellow box of the exercise, I want to ask you if you have any question. Any questions so far? Okay. I anticipate that in the next lecture, I will give a prize to people asking questions. I have to decide what kind of prize, but I'll do something. Okay, now let's pass to exercise. And let me open an R console. So the R console, it's here, R. This is my R console here on my PC in the office. And once again, keep in mind that I don't have the menus here because I'm not working on Windows. In Windows, you get the menus, but the console is identical. It doesn't make any difference. And I'm not sure if I already suggested to you to download and install on your PC RStudio. So today we are using the console, but before we move forward, let me start RStudio from here and let you know how to install it. Let me start from installing. I think I already mentioned this to you, but let me just make a quick reminder for those that maybe didn't know it. In Google, if you search for RStudio, you get a free download here. And if you click on the first link, 1 second, okay. Install RStudio. Let me see. Here you have all the platforms, okay. You just have to download the installer and installing it, okay. And if you, after installing it, if you start RStudio, which once again, we are not using it today, but I just want to show you how it looks. you get something like this. And it's not necessary that you follow me, okay? Office, let me see where is development, RStudio, here it is. 1 second, because you don't see it. You still don't see it, 1 second. Okay, okay, and let me show it to you. This is RStudio, and you see the console, it's here below. And we can expand it. This is the console of R. What is the usefulness of this platform? It is a platform that makes the use of R more user-friendly. The usefulness is that you have not only one window with the console, but several windows. And these several windows help you in visualizing several things together. So just to give you an example, if I define a variable a equal 1 in the console and I press return, you see that in the upper right window, I get now a list of the variables that I defined, which is, useful. And another thing, let me generate now a vector. So the vector may be, let me call it v equal to, and the vector is generated through the function c, and in parentheses, in round parentheses, I show you, I need to put the elements separated by commas. And then you see here that v is numeric with, it's a vector with these elements. Now, something that you don't know, in the console, if we plot the vector, we just give the instruction plot v, we get here a plot, a very basic plot in the plot window. So RStudio allows you to show all together the console, a window with a list of variables, and the plot window, if any. You can personalize these windows, so you can play with them. And there is an extended list of menus, many more than the menus that you get from the console alone. So for instance, if you look at edit here, this is not very useful, just 1 second. Here there is a menu session, and one interesting thing here is set working directory. So you can set where the R data are saved. You can set the directory. You can do it also through the console, but here it's easier. You have the menus. And one important thing is under File, Import Dataset. This allows you to import data in R, which is one thing that is not really user-friendly if you use the console alone, okay? Okay, so please, if you didn't install it so far, install RStudio. We are not using it today, so I am quitting. You see that in the console, I wrote Q with a double parenthesis. I am quitting. But in the future, we will use it because it's easier. It makes the use of R easier. I'm not using it today because I don't want to introduce now an additional complication. Now we are still at the basis of R, and the basis, in my opinion, should be studied, should be learned on the console. So I don't save my workspace, and then it disappeared, and I have back my previous console. Let me define in the console a vector like I did before, okay? And just by chance, I'm typing numbers. Okay, and let me plot it to see what happens. Now, by plotting, a graphical window will be open. You don't see it on my screen, it's here. It's a separate window, which shows to you the graph, okay? It's a very trivial one. Of course, you may say now, Excel is much better. The graph in Excel looks much better, but this is the basic one, and I can specify many additional parameters. And this graphic window can be saved in a file. We don't do it now. And can be closed. If you close it, it's no problem at all. The console remains open. Okay, now what is our task now? Our task is to move forward, learning something more of R in order to be able very soon to make an analysis, to make some exercise. Okay, so to start, I think the best way, or let's say the most efficient way to learn something related to information technology, in my opinion, is to start using it. And if you start using it, you get information on what you need for your specific purpose. Of course, this is not probably the most recommended approach because if you are a beginner, probably the most recommended approach would be to start by reading tutorials which introduce you step by step to structured learning. And the structured means that you have a learning process. You get entertained into a learning process that is comprehensive. It's not just focused on what you need. On the other hand, this approach takes more time. So I prefer, by assuming that you have some experience already, some digital experience already, I prefer to start with an application. And if we go back to my website and you go back in the same page which we discussed in the same lecture note that we discussed earlier, there is an exercise that is proposed here. And you see computation of statistics and use of statistical software. So let's use this one, okay? So let us suppose that we measure daily max temperature at a location for a duration of 10 days. Of course, such a duration is not long enough to assess climate. It's just an exercise, okay? It's just an example. And we collected the following numbers, 20, 22, 17, etc. So we can use the R software to draw a graph of the data. First of all, we need to input this data into R, okay? And here you see the instruction, the suggested instruction. You see, it's the definition of a vector named temperature. We can cut and paste it. This is the first message that I want to give to you. If you select the instruction, copy it with I'm just copying by right clicking on it, right clicking on the selection. So I right click on the selection, copy, and then I need to switch to the R console. Here we are. And then I can right click, paste, and then I press enter. So temperature has been included. Let me clear my screen, Control L. If I now want to see if the vector was indeed recorded, I can show it. And to find a variable, it's just enough that I write the first 2, 3 letters, and then I use the tab over the keyboard. The tab is on the left of the keyboard, is usually marked with 2 arrows opposite each other. And you see that if I press the arrow once, I got a P, a letter P, and nothing more. It means that there are probably 2 alternatives. Let me just press the tab twice, and I get the alternatives: temp file, temperature, temp dir. So let me just write temper and then the tab again, and I get temperature. That's it. And I pressed enter to visualize it. So why it's important that you know the shortcuts. because in this case I used a shortcut. Let me do it again. Temper and then tab. You see that the tab allows me to complete the name of the variable, and then I press return. So why, once again, do you need to know the shortcut keys? So the use of the tab is a shortcut, what in Italian we call scorciatoia. They are extremely important. When you work on the PC, you have to learn the shortcuts because they allow you to save a few seconds. So you may say a few seconds, who cares? Yeah, but when you work on the PC as an engineer, you may repeat the same operation like 1,000 times in a day. So if you save 3 seconds each time, at the end of the day, you save an hour. And this hour is extremely important. Why? Because you can relax, you can drink something, you can sleep, or you can socialize, or you can deliver your work earlier than others. And all of these things, which, by the way, are achieved, maybe achieved more than one together. You deliver your work first, and then you may relax, are extremely important in order to, in a way, to optimize your working performances. Efficiency is something that the employers appreciate very much. So try to learn different alternatives to perform your job, and try to learn all what may allow you to be more efficient, because, as I said, this is extremely important. Okay, now that we got the vector with temperature, let's go back to the website in order to plot the graph. And this instruction, which I'm copying and pasting, it's nice because it delivers a great amount of additional information. Let me copy it. I right click on the selection, copy, and I switch to the R console and I paste it. Okay, so let's read the instruction. Plot temperature. This is something that we already know. In the past, a few minutes ago, we did plot vector v. Okay, plot temperature, but then there are additional arguments to the function plot. The function plot accepts additional arguments. The first argument that I need to give is the name of what I want to plot. In this case, it's the vector temperature. And then I can give the labels for the axis, label for the x-axis, days, label for the vertical axis, the y-axis, daily maximum temperature, type equal both, equal B. What does it mean, both? Both point and lines. Color, red. If I press enter, I get this graph here, which you see, it's already a little bit better than what we got before. I have a label in the axis. I have displayed both points and connecting lines. It's a bit better. And if I go back to the R console here and I type something like grid, I get also the grid. So it's becoming nicer and nicer. And if I go here and I write title equal, I think it is like that. Title temperature. I'm not sure of the syntax. We will see. Yeah, it's here. Let's go here. You see that I can embellish this graph, and R is very much sophisticated in terms of plotting. We are only using the basic function of it, but still you see that it's we are already getting something interesting here. Okay. Now, next move. Let me devise a new exercise. And the idea is, let's go to the Atlas Old World Drought Atlas, download a time series, upload it in R, and make a graph. This is becoming more complicated. First of all, let's go back to the website and the Old World Drought Atlas. Any questions so far? Am I too fast? Am I too trivial, too slow? So please let me know any possible suggestion, okay? Just, I am very much interested in getting the feedback, okay? So if you, for some reason, sometimes some of the students in the past suggested to me to make the exercises in presence. Other students said that it would be better to make the exercises online because, you know, in presence, it's a bit of a problem because you need to bring your PC. I don't have a lab where I can go. So I'm sticking on the use of the online hours for exercises, but I really would like to know if someone is getting lost. If you feel shy in writing on the chat, you can write a private message to me through Teams, or you can write an email. The email, I'm not reading emails right now. So if you want that I read something directly, you can send a private message over Teams, like, Professor, I'm sorry, really, I can't follow you because you are too fast. Okay, perfect. Let me know, okay? Or, Professor, please, it's too trivial. Okay, could you explain the type B? Perfect. This is a very good question. So you win the first prize, okay? And in presence, if you're attending in presence on Monday, I will give you a prize. Let me just see because I'm not sure. Okay, perfect. Okay, let me call back the instruction plot. With the arrow up, I'm calling it back. Okay. The last one was I pushed the arrow up on the right of the keyboard. And the last one was temperature. The last but one was grid. And the last but two was the plot instruction. And let's drop type B. I am dropping it. Okay, good. Let's see the graph. What is the result? You see that I have only points, no lines. Okay. Let's go here and let's use now type L. Now I get only the lines. Let's now write type E. I get only the points again, so this is the default. This is the same result that I get if I don't specify the type. If I put type equal both, I get both of them. So I hope it's clear. But your question is very good because it gives to me the opportunity to also specify to you how you can find the additional options of the plot function. Okay, additional options. So let's call the help question mark plot. This is the help that you can see on my screen and you can get on your PC. So this is the usage, plot XY. X is needed, Y is not needed, because if you give only X, like I did for the temperature, you get a plot of equally spaced points. If the points are not equally spaced, you need to give both the coordinates, X and Y, okay? And you see that there are some dots arguments to be passed to the function, to methods, such as graphical parameters. Many methods will accept the following arguments. Okay. Type. What type of plot should be drawn? Possible types are P for points, L for lines, B for both, C for the lines part alone of both, O for both overplotted, H for histogram. Okay, so this is interesting. We will try the histogram later on. S for stair steps, capital S for other steps, All other types give a warning or an error. Okay, good. Main, an overall title for the plot, see title. So the title can be given with a separate and subsequent instruction, as I did, or it can be given by using the argument main here, sub, a subtitle for the plot, xlab, which I already used, a title for the x-axis, ylab, a title for the y-axis, asp, the y-x aspect ratio, see plot window. Okay, an interesting thing here, we read cpar, graphical parameters. This is only a first list of graphical parameters. There are many more. Okay, let's see par, question mark, par. Okay, par can be used to set or query graphical parameters. Let's look at the list of the graphical parameters. Here you have a long list, okay? And the long list is here actually. Here it's the long list, graphical parameters. And these are interesting because these are high level parameters. You can really obtain very nice, good looking graphs if you use these parameters, background color and a numerical value giving the size of the font, etc. And let's try to use some of them. And 1 second, okay, checks. Okay, let's try to use some of them. I go here and let's clear the screen. Let's call the plot function. Plot temperature, type equal both. Okay, let's write here type equal H, color red. And let's write here checks dot lab equal to, and let's see what happens. Okay, this is the histogram, and you see what happened. The label of the axis are bigger, and this is the effect of this instruction. 2 means it's a magnifier. I could have, because they are maybe too big, 1.5, and here you see that it's a little bit lower size. What I can see here is that the label of the y-axis is too close to the limit of the plot. Sorry, we can adjust this. Okay, we are not now focusing on this because I don't want to focus on graphics only. Okay, good. Now, any other question? Perfect. The drought atlas. Let's see if we can download quickly a time series. I think this would be a nice experiment. So let's take again the reconstruction and let me do what I did before. 2012, okay. And let me go to somewhere here in Italy and let's take the time series. Okay, and let's take the data time series okay, here it is, download txt. I select download the text file because the other downloads are for figures. Let me see if it works. I think yes. Let me open it. 1 second. Let me try to open it because I need a file manager. Because the data was saved through download, I need a file manager. Just 1 second. And let me see if how it is. Okay, very good. It's a bit complicated. Let me show you. And this is a text editor, like Notepad in Windows, through which I can see the data. it is saved as a text file. What is a text file? A text file is a format for writing data that can be read by any program, maybe Excel, maybe whatever. And you see that we are interested in the year and the PDSI. Now, the problem is how to upload this file in R and how to upload it. I think if you are working in Windows, I'm not sure if you followed me in downloading the data. If we want to upload it in Windows, you have to save this file in Documents. In Mac, I'm not sure where it should be saved. I think you can save it on the desktop in Mac. In Windows, you should save this file in Document, and I know in Linux where I should save it. So let me now explain to you how to upload a text file into R. Look, with RStudio, this is very easy. But I don't want to use RStudio today. From the next time, we will use it. Today, I want to use only the console. So I want to anticipate that uploading data into R, if you use the console alone, it's not so easy. It's not so easy. And let's try to do that, okay? So I close this file because I don't need to see it again. And I get back into my R console. Let's clear it. And let's define the name of the variable, the name of the vector of the PDSI. So PDSI is equal to, and then I need to upload the data from the file. So scan means scan a file, please. Get numbers from the file, okay? Okay, scan, and then I need to give the file name. So probably you are allowed, if you put the file into Documents, you can just give the file name here. And in my case, the file name was, one second, this one. The file name was this one. Oops, sorry, not this. Let me get the file name. And I'm getting the file name with the file manager. I don't understand why it's not 1 second. Okay, give me 1 second. Okay, now it should go paste. Okay, this is my file name, okay? And it should be given between double commas. So if you save the data into Documents, this instruction should work. In my case, I didn't save in my analogous document folder. So if I write return, I get a file not found. Okay. So this happens if you in Windows didn't save the file into Documents. Okay, so what is missing here? The path, the location, the name of the folder where the file is stored, is saved. In Windows, by default, R is looking into Documents. So if you put the file there, this is why I told you, if you put the file there, no problem at all, you get it. In my case, it's stored in a different folder. Let me just write here where it is. So it is my path to the folder is home. And of course, it's not the same path for you. Don't write what I'm writing, because if it's not in the document folder, you need to write your path. in my case is downloads, yeah, downloads, and OWDA reconstructed, and that's it. With the tab, I completed it. I am aware that what I'm doing is not really straightforward, okay? So don't be concerned. If you have any problem, if you are trying to reproduce it and you have any problem, on Monday, I will ask you at the start of the lecture if you experienced any problem on that. Here, and then if you had any problem, we will solve it together. Here, the problem is the path. It's this part here that for me is the path to the file. For you, as I said, if it is in documents in Windows, you don't need it. Otherwise, if you are in Mac, or if you are in, if you save the file to a different location other than documents in Windows, you need to give the path. And it's not straightforward in Windows to find the path. In Linux, it's straightforward. In Windows, not. Now, there is another argument that I want to give here. I remember that the file, I want to show it to you again. This is my file. It's composed by numbers, and these are what I want to upload. But there are 3 lines that contain text. I need to skip it. Okay, I need to skip it. I anticipate one other thing. Sorry, because I want to look at the chat. I don't think so. I mean, the question in the chat is, isn't it possible just to grab the file and bring it inside the Arduino to get the path? I'm not sure. I'll try later. Okay? And as I said, as I was saying, I have to skip 3 lines. I have to tell R to skip 3 lines. Otherwise, it gives an error because it is expecting numbers and it finds characters. And another thing I want to anticipate to you, you see that digits are separated by the point, not the commas here. If your Windows is set as with the comma as digital separator, you get an error. So you have to make sure that either you set Windows to use the point, I give you the suggestion, as digital separator, because it's an international standard, or you have to make a find replace in the file and substitute the point with the comma. What I suggest to you is to set your PC so that the digital separator is the point. It's an international standard. But what I need to give here, it's an instruction skip equal 3. So let's see if I can upload the file. Yes, I uploaded it. Now, the problem is that the file was uploaded as a vector. And let me just show you the first 10 elements of the vector. 110. Look at the instruction. If I want to extract elements from a vector, and in this case, the elements from 1 to 10, I need to give between square brackets the range of the elements I want to extract. So what you can see here is that actually I uploaded something that is a matrix, and I got a vector. This is a bit of a problem because you see that the first number is the year 1000, the second number is the PDSI, the third number is the spline, which we don't want to lose time to understand what is. And then the fourth number is again the year. So I need to put this vector into a matrix, okay? So how can I do this? And then give me 3 minutes and then I'll stop. And give me 1 second, because before showing to you how connection lost, let me just check. I don't think so. Are you still listening to me while I make my trial? Just let me know. And Yeah, okay, there was probably a problem with one person or a problem with me. Just 1 second, because I wanna make an experiment before I show to you what I'm doing, because I don't want to create confusion. Give me 1 second, and then 3. Okay, let's see. One, 10, 3. Okay, good. Okay, here is my console. I cleared the screen. So let me clear the screen. Perfect. Okay, so I got the vector PDSI, and 1 second. You see, I need to transform it into a matrix. So let me create a matrix which I call the PDSI1 from the vector PDSI, and the instruction is array. So create a matrix, and as arguments I give use the data from PDSI, and the dimension of the matrix is given by the vector that is given by the vector 3, and I think the dimension of the I don't remember what is the length of the vector, so length PDSI divided by 3. So what I wrote here is literally create a matrix called PDSI1 by using the vector PDSI, and the dimension of the matrix is 3 columns, and a number of rows which is equal to the length of PDSI divided by 3. Let me see if it works. Good. Now, let me try to extract PDSI1 first column and rows from 1 to 10. Good. I have the years here. Good. So I obtained my purpose. And if I want to visualize the matrix, what I can do is to write this instruction. So visualize PDS1, all the columns, rows from 1 to 10. Okay, actually rows and columns, okay, you can see here, okay, the data. Now, last thing, and then I close. Let me make a plot. And now I need to give a XY plot. So the X is PDSI 1 comma, which means first column, all the rows, and the Y is PDSI 1 2 comma. Okay, and then let me write type equal both, col equal red. Okay, and xlab equal year, ylab equal summer PDSI. Let's try to press return. PDSI1, yeah, is correct. Sorry, I forgot here I. Okay, let's see the plot. And here is my plot. Okay, with the awareness that I made leap step forward, a giant leap step forward, which means a gigantic step forward in terms of complexity. So with awareness that some of you may be a little bit lost in the process. On the other hand, keep in mind that if you digest, if you are able to reproduce what I did, we really made also a giant step forward in our understanding of this program, because we learned how to upload data, how to make quite complicated graphs. Let me put a grid also here. It's already a quite nice graph, quite good looking. Okay. Now we are done. Let me exit from R and save it. So I use the function Q and to round parentheses, save workspace, yes. And here we are. Okay, now let me stop the recording. 1 second, stop recording. Okay.